I'll just. So viscous fluids, we will learn about how the viscosity of a fluid affects its flow. We will, of course, first define what viscosity means, and then look at some aspects of viscosity and kinds of flow. So viscosity is related to shear stress and strain. So remember when we were talking about shear stress and strain, that was before the break. It's stress is force over area. Right? If you apply stress on an object, you're applying force over an area, surface area. And if you apply stress, there's a corresponding strain. The strain is the deformation that arises from the stress. Shear stress is the kind of stress where the force is parallel to the surface. That's when, for example, I push on this book. On the book surface, parallel to its surface, you can see how it's deformed. On the side there becomes slanted. Okay, so that's shear stress. Corresponding stress is force over area, and the corresponding deformation is the strain delta L over L0, how much deformation the object experiences. Now for fluids, you can think of shear stress and strain in a similar way. So if you imagine that the book covers are two plates, and sandwiched between those two plates is a fluid. Okay. If you apply shear stress on the top surface while the bottom surface is fixed, okay, and the pages here you can imagine as the fluid on top, you will see that the fluid on top will move faster compared to the fluid at the bottom. So notice how when I apply the shear stress, the pages on top sort of move, okay, parallel to surface, while the pages at the bottom do not really move that much. So in fluids, you can think of that similar way. There's a shear strain that accompanies, that's a result of the shear stress applied to the fluid, except that in fluids, the shear strain, which we call shear strain rate, relates to the speed of the fluid. Okay. The speed of the fluid and this length over which the fluid occupies. Okay. Right, so from that concept, we can define viscosity as shear stress over shear strain. And we use this symbol eta for viscosity. So another Greek symbol. We're collecting all Greek symbols. Right, so this is a Greek symbol which we read as eta. Okay. It's not the ETA chips, it's the eta. Fancy letter N. It's referred to as shear stress over shear strain. If you remember, we talked about Young's modulus when we were talking about solids, and we said that Young's modulus is the measure of the material's resistance to deformation, and the larger the Young's modulus, the more difficult it is to deform the object. Right? Yeah. So, and we looked at this example of the bungee cord. The bungee cord has a small Young's modulus because the bungee cord needs to stretch easily to avoid injury to the jumper. Okay. So that's a similar concept to viscosity, except that viscosity refers to the fluid. It's how easily the fluid can flow. So the higher the viscosity, the more difficult it is for the fluid to flow. Just like the higher the Young's modulus, the more difficult it is to deform the solid objects. The higher the viscosity, the more difficult it is for the fluid to flow. If you look at this equation for viscosity, stress over strain, stress is force over area. This is essentially stress. And strain rate is velocity over the length L. If you rearrange this equation, you'll see by multiplying both sides with V over L, you'll see that force over area is equal to viscosity times V over L. So what this tells you is, okay, the higher the viscosity eta, you need to exert more force in order for the fluid to flow with a certain velocity V. And you can sort of imagine that. Viscosity, you can sort of roughly say it's how thick the fluid is. Okay. So the thicker the fluid is, the more force you need to exert in order for that fluid to flow and have a velocity V. So imagine water and honey. Which one is more viscous, water or honey? Honey, it's thicker, it's more difficult to flow. Okay? And so if you wanted honey to flow at the same speed as water, you need to exert more force on the honey to make it flow at the same speed. Right? Okay, so that's the concept of viscosity. Right, so looking at the workshop problem on viscosity, they have their many snakes produce venom. They deliver that venom via sharp fangs, and the fangs can be modeled as hollow tubes with length 2 centimeters and radius of 1 millimeter. So that's for the cylindrical fang, for the hollow tube, like shown here. Now, a scientist places the venom into an instrument called a rheometer, in which the venom sits between the inner wall of a cylindrical container and the outer wall of a rotating cylinder. Right. So the first question says that to keep the surface of the rotating cylinder moving at a speed v relative to the container wall, there's a continuous force applied tangentially at the rim. By measuring force for a given velocity, what property of venom does the rheometer measure? What's the property of a fluid that's related to how fast it can flow and how much force you need to exert to make that fluid flow? We just learned about it, viscosity. Okay. Essentially, the rheometer wants to measure how thick the venom is by exerting a given amount of force. Okay. The more viscous it is, the more force should be exerted to maintain the speed. Right, so it says, so that jumps to the next question. To keep the rheometer moving at a speed v, let me just change this. Yeah. So so for a given speed v, more force must be applied. How would the scientists compare venom with water? Which one is more viscous? Venom. If you need to apply more force to keep the venom moving at the same speed as water. Okay. And assuming that venom is Newtonian fluid, okay, we'll go to Newtonian fluids in the next slide. But when we say Newtonian fluid, the viscosity does not change. Okay, so assuming that the viscosity is constant, how would the tangential force required to maintain the cylinder change if the speed was doubled? So you have this viscous venom. You want to make it move twice as fast as it normally does. How much force should you apply relative to the original force? Double, yeah? Because how much force determines in direct proportion, how much force directly affects the speed of the fluid. So if you double the speed, you should double the force as well. All right, so we can therefore classify fluids into two types. So whether the fluid is viscous or non-viscous. So when we say the fluid is non-viscous, the fluid flows easily and it flows with uniform velocity. So this figure here shows you that the fluid flows all together with uniform velocity, but with viscous fluids, it's more difficult for the fluid to flow, but at the same time, the velocity is non-uniform. In fact, in the middle, the fluid will flow faster. Okay. And because the fluid is, and because viscous fluids, for viscous fluids, it's more difficult to flow. A pressure difference is needed to make them flow, or at least some force is needed. So related to the ketchup analogy, you need to exert some force to force that ketchup to flow, to tomato sauce or ketchup. Yeah, right. So for viscous fluids, the key thing is you need a pressure difference to overcome the viscosity, and that will allow, the pressure difference will allow the viscous fluid to flow. And that concept is called Poiseuille's law. Well, I don't know how to pronounce that word. Yeah, just in order to say it, let's call it Poiseuille's law. Yeah. Mathematically, Poiseuille's law is given by this equation. Okay. Is it another scary equation? Yeah, we'll dissect that equation. It's probably not as bad as you think it is. We'll look at an example later on. But Poiseuille's law describes the flow rate. So it's how much fluid flows across a surface, right? And it's related to the pressure difference because it's a viscous fluid. Right. So two ends of the path should have different pressures. The fluid will flow, and therefore, as the fluid flows, it will have a flow rate. And that's why the flow rate is related to the difference in pressure. So Q is flow rate, volume flow rate, which is volume over time, or area times speed. R, that's the radius of the pipe where the fluid is flowing. Eta, that's the viscosity of the fluid. It's a property of the fluid. L, it's the length of the pipe where the fluid is flowing. P1 and P2, they're the pressures at two different points. And remember, for a viscous fluid to flow, you need to have a pressure difference, and that's P1 minus P2 is the pressure difference. Okay. Right. Notice the radius is raised to a power of 4. Okay, be careful with that. That means that if you double the radius, that will be 2 raised to the 4, and that will be 16 times. We will look at an example with that. And the second question in the workshop, when biting, the snake only has about 100 milliseconds to inject enough venom to stun its prey. To maximize the volume delivered in this time, an individual snake would have the biggest advantage if, and you're given 4 choices here. Which of these will make the flow rate bigger because flow rate equals how much is delivered per unit time, right? So if you want to increase the volume, so if you want to maximize the volume delivered, you need to maximize the flow rate. Okay, flow rate is related to the volume. Okay. So I'll let you think about this for a few minutes. Right, so flow rate equals volume over time, and that's what we want to maximize the volume. But venom is also viscous. Okay? And so you need a pressure difference across the fans in order for venom to flow. And yeah, the pressure difference is related to the flow rate via Poiseuille's equation. So P1 minus P2, that's the pressure difference across the fans. There should be a pressure difference across the fans so that venom will flow out the fans. Otherwise, it's just a viscous fluid that's sitting there. Okay. All right, so let's dissect that equation. So you must maximize Q, the flow rate. Okay. What will happen if in the first part, the pressure difference is twice? Okay. Right. If the pressure difference is twice, it's doubled. So it says here, the pressure is twice. That means pressure is twice. What will happen to the flow rate? It will just increase by a factor of 2, right? Pressure is doubled, flow rate will double, correct? Yeah. Next choice, the radius is twice that of a regular snake. Okay, so the radius is doubled. Okay, means 16 times because that's 2 raised to the power of 4. Okay, so double the radius, the flow rate will increase by a factor of 16, 2 raised to the 4. Okay, the length is twice, so the length is longer. What does it tell you? Poiseuille's equation tells you that if the length is doubled, the flow rate is actually halved, right? Because length is there below. And also, if the viscosity is doubled, the flow rate is actually halved. Okay, so which snake will have the biggest advantage? The snake with what's this? Bigger fangs, meaning wider, bigger radius. Okay. All right. Sounds okay? Yeah. So yeah, that's conceptually dissecting Poiseuille's equation, what each term means and how it affects the flow rate. Now let's look at this numerical example with drug is delivered to a patient via a syringe. The syringe is a 0.05 meters long or 5 centimeters long, and it has an internal diameter of 1 millimeter. That means 0.001 meter internal diameter, and it delivers the drug at a rate of 10 millimeters per minute. And we want to find the flow rate, given that the drug viscosity is this 8.9 times 10 to the minus 4, we want to find the pressure difference in the syringe. Okay, so flow rate, that's the volume over time. We're actually already given that it flows at a rate of 10 mils per minute, 10 millimeters per minute. And flow rate is volume over time The volume is 10 milliliters. The time is 1 minute. So it's, again, just a business of converting units, converting milliliters to meter cube and minutes to seconds. So milli, the prefix milli is 10 to the minus 3. So that means 10 milliliters is 10 times 10 to the minus 3 of a liter. And you need to convert liters to cubic meters. So in the end, you have 10 times 10 to the minus 6 cubic meters for the volume. And the time, 1 minute is 60 seconds. So you do the calculation, volume in cubic meters divided by the time in seconds. And you have this flow rate of 1.67 times 10 to the negative 7. So now that you know the flow rates, you can solve for the pressure difference across the syringe. Okay. Poiseuille's equation relates the flow rate to the pressure difference. Okay. You need to rearrange this equation because you want to find P1 minus P2. It's the whole P1 minus P2 that you want to find. It's the difference in pressure across the syringe. Okay. So you rearrange your equation and you actually have everything because the problem gives you the length. You need to convert that to meters. You've solved for the flow rate Q. The viscosity was given in the previous slide. And the radius you can, so R, that's the radius you can get from the diameter. Okay. So if this is the circle, the diameter is the whole length here. That's the diameter. So therefore, if that's the radius will be half the diameter. So you can get the radius from the diameter. And you have everything that you need to solve for the pressure difference, which is around 302.7 pascals. Any question about Poiseuille's equation? So maybe it doesn't look so scary after all, I hope. Maybe not as scary as Bernoulli's equation. Yeah.
Can you give us lectures for these? Because they're not on the lecture slide for the final one.
Yeah, I post my lecture slides with the annotations right after the lecture because I include the annotations that I do in class. And then you will also have access to the video as well, to the lecture video that I've recorded. All right, so we know viscous fluids will need the pressure difference in order for them to flow. And there are two kinds of flows. We can classify them as either laminar or turbulent. The main difference between laminar and turbulent is the speed for which the fluid is flowing. In laminar flow, the fluid does not flow so fast. It's flowing at a low speed. So pressure, density, and velocity is constant in time, and you form these streamlines. But in turbulent flow, it's because of large fluid speeds, and you have this, rapids and vortices. Okay. So again, hookah falls. Okay. Just before you have this drop in water, just before the waterfall, you can see how calm the water is flowing. That's laminar flow. When the water becomes turbulent, that's when you have turbulent flow. Okay. How can we determine whether the fluid is flowing with a laminar flow or a turbulent flow? That is determined by this quantity called Reynolds number. Okay. So Reynolds number RE gives the flow rate for when turbulence occurs. Okay. To determine whether it's turbulent or not, just solve for RE. It's just a number without any unit. If the Reynolds number is greater than 3,000, you have turbulent flow. If Reynolds number is less than 2,000, you have laminar flow. And there's a gap between these numbers. So between 2,000 and 3,000, you have this interchanging turbulent and laminar flow. Okay. Let's look at an example. Maybe it's better to look at an example. So in the previous example with the drug delivery, determine whether the flow of the drug is turbulent or laminar as the drug is injected through the syringe. Okay, so we're given, we already solved the flow rate from the previous problem. The diameter of the syringe was also given in the previous problem. The viscosity was also given. The extra information that we're given is the density of the drug that's being delivered. Okay, so Reynolds number needs the density, the diameter through which the fluid will flow, the cross-sectional area, the viscosity, and the flow rate. Yeah, as I mentioned, we essentially have these information. We can solve for the area because we're given the diameter. We can approximate the syringe to be cylindrical, and the cross-sectional area of that is a circle. The area of the circle is pi r squared. The radius is half the diameter, so that's 0.005 squared. We can get the area in short. Okay. So density of the drug was given, the diameter of the syringe was given, flow rate we calculated earlier, viscosity was given. Oh, sorry, this is area, which we solved here, and viscosity, which was given. And you get a Reynolds number that's 251. So is the flow turbulent or laminar? Laminar. It's less than 2,000, so it should be laminar. If Q is increased to 250 milliliters per minute, meaning a factor of 25, then will the flow be laminar or turbulent? So everything is kept constant. Density, diameter, area, and viscosity, they're all the same. Only the flow increases by 25. So if the flow increases by 25, that means that the Reynolds number should also increase by a factor of 25. Right. So increasing the Reynolds number by a factor of 25 means you multiply the original one with the factor of increase. Okay. So in this case, will the flow still be laminar or will it be turbulent now? Turbulent, because its Reynolds number is more than 3,000. Yeah. So that's essentially how you apply Reynolds number. So maybe it's not as scary as it looks like. Yeah. Okay, and just to wrap up, let's look at these workshop questions, the last one. So here we're given that the pressure in across the fangs of the snake is 6660 pascals. I'm sure that's just a coincidence with the 666. But yeah, the flow of the venom is characterized by a Reynolds number of 21. So is the venom flow laminar or turbulent? It's a Reynolds number of 21, so that means it should be laminar. Laminar is characterized by these orderly streamlines. Okay. So this top figure shows a laminar flow. Turbulent flow Yeah, velocity vector is everywhere. Okay. Okay. And now the question, find the velocity at which the venom flows through the fangs when it bites into a lizard. So you essentially have the fang. It has a pressure difference, the pressure of 6660 pascals, and it bites into a lizard. The blood pressure of lizard is 20 millimeters of mercury. The viscosity of the venom is 50 millipascals times seconds. We want to find the velocity for which the venom flows. Okay, so let's sort out what's given. We know the pressure across the fangs, just given. The pressure of the lizard is also given in millimeters of mercury. So you need to convert that to pascals to have consistent units. Yesterday we saw that 1 millimeter of mercury is equal to 133.3 pascals. Okay, so 20 millimeters of mercury will be 20 times 133. You have now the pressure of the lizard in pascals. Okay. The radius of the fang was given in the original intro statement. The length of the fang was also given in the original intro statement. Now we're given the viscosity of venom. So velocity, there's a pressure difference between the fang and the lizard. So when the snake bites into the lizard, the venom will flow from the fang to the lizard because of that pressure difference. Okay? According to Poiseuille's law, that pressure difference between the fang and the lizard will cause the venom to flow at a flow rate of Q. So we can solve for the flow rate. We know everything, the radius given, pressure difference across the fang and the lizard, viscosity is given, and the length of the fang is given. We get the flow rate. The flow rate is related to how fast, volume over time, but also we have this alternative definition of flow rate of area times speed. So from there, you can get the speed. We can solve for the area. The speed is 0.5 meters per second. So, all right. Okay, so that's viscous flow. Yeah, I know we didn't get through the other sheet of the workshop problems. We can probably look at that during the revision week when we're looking at exam questions anyway. But you can try that out and I can post the solutions. But yeah, so otherwise there's the mastery test is due this Friday. You have labs this week, and so I'll see some of you in the labs. Otherwise, I'll see you next week. Work and until, yeah, I think Torques and yesterday's lecture also, some of yesterday's lecture. You're welcome. See you.